But what we're going to do now is I'm just going to kind of show you how to use calculus with our old physics. Now, to do this, we have to understand the true definitions of the material we've been working with. So, for example, velocity. All right, we always said velocity is your change in position over your change in time. What that really means in calculus terms is velocity is the rate of change. Why did I put a T there? Seriously, says the rate of change in your position divided by the rate of change in your time. So velocity is the derivative of your position divided by the derivative of your time. So dx dt. Acceleration is your change in velocity over change in time. So your acceleration is dv dt, the rate of change in your velocity relative to time. So if we look at some of our old equations, we can actually do these substitutions. So let's just take our constant velocity equation and let's make it not so constant. So in theory, you can say, well, my position is equal to my velocity times the time interval plus my initial position. So we now know that, well, that's for constant velocity, but your velocity might actually just be changing on its own. So this right here could be rewritten as dx dt times t plus x sub naught. So based on the information you're given, you can use your old equations and kind of manipulate them. We could use our velocity equation and say, well, velocity is equal to your initial velocity plus your acceleration times your time interval. Well, what if your acceleration's not constant? Well, then you can say your velocity is equal to your initial velocity plus, instead of acceleration, we could use dv dt. And so now we can start to bring calculus into it. So we can use other more complicated scenarios. Old equations are still viable, but we might be replacing what used to be a constant with now its own equation. We might have an equation that describes the acceleration of the object. Okay? So we can manipulate things as we need. Now, why is this helpful? Okay, well, let's just take an example. Let's say you are given this situation where velocity is equal to negative 10x squared. All right, that's the problem you're given. You're saying, well, here's the velocity of the object described in terms of its position, not its time, not its acceleration, just purely in terms of position. And we want to understand, well, let's say we had defined your position relative to time. Okay? Well, we're going to use the skill of replacing the concepts we know with their calculus analogs. Okay? Now, technically, this is called a differential equation. All right? So I'm going to write out this definition. Differential equation. You can take an entire class in this in college. So a differential equation is basically just an equation that has the function and its derivative in it. All right, so it's just a technical term. All right, you don't really need to know it, just need to be able to do it. So let's go about this using this understanding that we can replace ideas with our understanding of the calculus terms of those. So instead of this v here, I'm going to put, well, velocity is dx dt. And so now I've got negative 10x squared equals dx dt. Well, I now need to rearrange this so that it works for me. Okay, so I'm going to just do some algebraic manipulation. And let's have some fun. So I'm going to get all the like terms on the same sides. Basically, we're just doing our old school algebra. So now I've got dx divided by x squared equals negative 10 dt. All right, so I got the t's on the one side, the x on the other side. Now I can start moving forward. Now I'm going to kind of simplify my life here. I hate fractions. All right, and I like to use the power rule. So I'm just going to rewrite this as x to the negative 2 dx equals negative 10 dt. Now, when we do this, we have to remember something here. I just got to make a little note. Your dx and dt. So whenever you have those, differential pieces, they must be in the numerator. All right, so don't put, they can't live in the denominator. If they end up in the denominator like they were over here, you got to do algebra to get them in the numerator. All right, I mean, it's not a heavy lift, but it's something you got to keep in mind. So now that we have this, all we're going to do is we are going to integrate both sides. And if I do my power rule, that means I'm going to have x to the negative 1 over negative 1 equals, I'd pull out the negative 10. So negative 10, and then the integral of dt is just t. So I would have this as my equation. And then I can kind of clean that up some more. So I really just have x to the negative 1 equals 10t. Now, don't forget, whenever you take the integral, there is technically a plus c living here, but that really doesn't come into play in physics unless they specifically say you need to like derive something, and then they give you some case elements like, oh, when the position is 0, here's the value. Then you can calculate what c would have to be. But for the most part, we kind of ignore it. So don't worry about it. But this means that our final equation is kind of this guy right here. And we've written your position in terms of time. So that's basically the answer we're looking for. Like I said, unless they want to go super specific and they want to have you figure out that plus c element. But yeah, that's it. So we're going to just replace what we knew with the calculus tweak on it. And then we're going to be able to do more complex math with it, with examples where objects don't have constant velocity. They don't have constant speed. There's equations that describe the accelerations, just the acceleration is just 5. All right. So hopefully that made sense. Hopefully it was helpful. And I will see you guys in class.